Hi, welcome to a mini lesson on coordinate geometry. So a little bit of background about coordinate geometry. So of course, sometimes it's referred to as analytic geometry. It's the study of geometry using a coordinate system. It was originally invented or discovered or named by René Descartes, who was a 17th century French mathematician. And its importance is really that it provides a link between algebra and geometry. So it's a really, really powerful tool. So you can see this example here, a geometric representation of a circle on the coordinate plane. And then the algebraic representation of that circle is this equation, x squared plus y squared equals 9. So a lot of connections between algebra and geometry can be made using a coordinate system. So what we're going to do through this mini lesson is really focus on the distance formula, just to give you an example of coordinate geometry that really in the elementary grades starts with just understanding locations and the coordinate system, plotting points, that develops into these other ideas in middle school and high school. So here are some common topics: graphing points and lines, graphing curves, for example, parabolas and circles, graphing polygons, so that's the connection also to the elementary grades, graphing parallelograms, graphing rectangles, other quadrilaterals, and then in particular finding distance and midpoint formulas. So you should have printed out your deriving the distance formula activity sheet, and this is just a copy of the first page. So we're just going to go through this together. So you can see here is an example of a coordinate grid. We have two axes. The x-axis is the horizontal axis, and the y-axis is the vertical axis. I don't know why they're named that way. It's pretty arbitrary, but that's the convention that we use in mathematics. And then you can see the units, right? So in the x in the right is the positive direction, and then to the left is the negative direction, and for the y-axis, up is the positive direction, and down is the negative direction. So what we're going to do is we're going to use this diagram to answer some of these questions. We're going to talk through the first page together, and then I'm going to let you work on parts of it on your own. So for part A is asking what is AC. So you notice the notation here is the letters A and C with no bar above it. So you can see down here at F when it says draw segment AB. So that notation is referring to the actual segment, whereas this notation with no bar is referring to the length or the measure of that segment. So what we're looking for is an actual numeric answer. So of course we can find AC just by looking at this diagram, and we can count the units and see that the length of AC is 8. The coordinates of A and C, we can see that the coordinate of A is -3, 4. We always list the x coordinate first, so -3, 4 would be the coordinates for A. And the coordinates for C would be 5, 4. So notice that A and C have the same y coordinate because they're on that same horizontal line. Notice that when we counted that distance of 8, we can also notice that those x-coordinates also give us 8. So the x-coordinate of -3, that distance is 3, and that distance is 5. So the total distance is 8. And we can do the same thing for C and B down here on questions D and E. So for C, again, the coordinates are 5, 4. For B, the coordinates are 5, -2. So again, we can see that that distance is 7. I'm sorry, it's not 7, it's 6, because that is 4, not 5. I apologize. So the length of CB is 6. Now for F, when we draw a segment AB, so you can go ahead and do that on your paper, when we draw a segment AB, we notice that we are forming a right triangle. And we know that's a right triangle because AC is perpendicular to CB. In that triangle, AC and CB are called the legs, and AB is called the hypotenuse. And of course we know from the previous part of this lesson that because it's a right triangle, the Pythagorean theorem would apply. So that's what we can use to find the length of AB. So to do that, we would say 8 squared plus 6 squared equals AB squared. 36 plus 64 is 100. So the square root of 100 is 10. So the length of AB is 10. So what I want you to do now is pause the video and work through question 2. Okay, I hope you've had some time to work through question 2. So you can see we can create a right triangle with a horizontal leg and a vertical leg that has hypotenuse AB. And then that right angle would be vertex C. We could also draw a different triangle from the one that I have here. If you located point C at -2, 3, that would give you a congruent right triangle. We can use the strategies that we did in part 1 to find the lengths of AC and CB. And if you do that, you notice that AC is 7 and CB is 5. And then all we're doing here is applying the Pythagorean theorem to find the length of AB. So 5 squared is a leg, 7 squared is a leg, AB is the hypotenuse. AB squared is 74. So in order to find the length of AB, we would undo that squaring or take the square root. The square root of 74 is approximately 8 6/10. Okay, again, pause the video and work through question 3, and then we'll come back and talk about it. So question 3, notice that the coordinate grid is different. There aren't distinct units. The units aren't marked. The axes aren't even marked. So we don't really know what is the x-axis and the y-axis. And this is done on purpose because what we want to do at this point is we want to generalize that idea of applying the Pythagorean theorem to find the length of the segment. So we're going to do that by using these general points, x1, y1, and x2, y2. So you can see that the coordinates of A are x1, y1, and the coordinates of B are x2, y2. And again, it's done on purpose, so now instead of counting from A to B, we need a systematic way to find that length. And if you notice from the first 2 problems, the way that we can do that, because it's a vertical line, we notice that the x-coordinate is the same. So we can express the length of AB by subtracting the y-coordinates. So you can see in part B, one way to do that is subtracting y2 minus y1 or y1 minus y2. Notice these bars. That notation is called absolute value. And you're going to see that in the next part. So the reason why we use absolute value is because distance is not negative. So for example, in part G, I notice that my y1 is 12 and my y2 is -22. It doesn't matter the order that I subtract those to find the length. But notice if I subtract -22 minus 12, that's -34. I know that distance can't be negative, so that absolute value removes the negative and just looks at the distance between those 2 points. So we can say that GH is 34 units. Okay, again, pause the video and work through question 4. So question 4 is just like question 3, but now we're focusing on the horizontal piece. So again, we have arbitrary points for C and D, x1, y1, and x2, y2. Since CD is a horizontal segment, then we know that those y-coordinates are the same. Therefore, we can express the distance between C and D by subtracting the x-coordinates. And again, because we don't want that distance to be negative, we're going to use absolute value. And then in our example, we would be focusing on the x-coordinates, -10 and 24, to see that EF also has a length of 34 units. Pause the video and work through question 5. Okay, a lot of information here in question 5, because what we're trying to do is come up with a general rule for finding the distance between any 2 points. Remember, if we can form a right triangle, then we know we can apply the Pythagorean theorem. So that's exactly what's happening in part A. We know that since we have a right triangle, PQ squared is equal to the sum of the square of the two legs, PR squared plus QR squared. Then, given what we just did, for part C, we have two expressions that we can use. For PR, the horizontal leg, we are subtracting the x-coordinates. And again, this order doesn't matter. For QR, since it is a vertical segment, we're subtracting the y-coordinates. Now, part D is just having us think about squaring versus absolute value. Whenever we square a number, the result is always positive. So what we do in this notation, instead of using absolute value, we just square. Since that's part of the Pythagorean theorem, we don't need the absolute value anymore. So for part E, the formula that we get, PR squared, we know is equal to, PQ squared, we know is equal to PR squared plus QR squared. The expression we have for PR is x2 minus x1 squared, and the expression we have for QR is y2 minus y1 squared. So if we just want to know the length of PQ, we're going to take the square root of both sides. And that's this expression in F, which is the distance formula. In part G, we're applying the distance formula given these 2 points, I at 8:12 and J at 2:4. Notice we don't have to memorize this formula. If we can remember that we're applying the Pythagorean theorem, which is what I have done on the left side here, draw my right triangle, I can think about what is the length of this segment. Well, I know this horizontal segment, I'm going to be focusing on my x-coordinates. 8 minus 2, that's 6. For the vertical segment, I'm focusing on my y-coordinates. 12 minus 4, that's 8. And then I'm just applying the Pythagorean theorem. And that's exactly what's happening here with the distance formula on the right. So here you can see x2 minus x1 squared plus y2 minus y1 squared. And when we simplify that, we can see that ij is equal to 10. So what we did is we applied the Pythagorean theorem to derive the distance formula.